Welcome to DES Encryption. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, we're going to explore the Data Encryption Standard, or DES, using simple numbers and examples. DES was the gold standard of encryption for over 20 years, protecting everything from ATM transactions to military communications. But today, it's completely broken. I'll show you exactly how DES works and why it failed. Think of DES as the grandfather of modern encryption. It pioneered many concepts still used today, but like a 1970s car without airbags or anti-lock brakes, it lacks the security features we now consider essential. We will use small numbers to demonstrate the clever techniques DES uses. See why a 56-bit key seemed huge in 1977, and understand how Moore's law turned DES from unbreakable to trivially breakable. This is a story of brilliant cryptography defeated by the relentless march of technology. The history and context. Let me take you back to the 1970s. IBM had developed an encryption algorithm called Lucifer for banking. The U.S. government, recognizing the need for a standard encryption method, asked the National Bureau of Standards, now NIST, to evaluate it. After modifications by the NSA, which caused controversy, it became DES in 1977. The numbers on the slide tell the story. In 1977, with computers trying 1 key per second, breaking DES would take 2.3 billion years. That seemed like forever. Banks, governments, and businesses adopted it enthusiastically. Your ATM card, for instance, used DES to protect your PIN. But look at what happened. Computer speed doubles roughly every 2 years. Moore's law in action. By 1987, that 2.3 billion years had shrunk to millions. By 1997, 2000s, the writing was on the wall. The real shock came in 1998. The Electronic Frontier Foundation built DeepCrack. This special-purpose computer could try DES keys per second. It cracked a DES encrypted message in 56 hours, proving publicly what cryptographers had warned: DES was no longer secure. Today, a few $1,000s of graphics cards can break DES in minutes. What seemed like an unimaginably large number of keys in 1977 is trivial for modern computers. This is why key size matters so much in cryptography. How DES works: the basics. Let's understand how DES actually works by starting with its basic structure. DES takes a 64-bit block of data, that's 8 characters or bytes, and scrambles it using a 56-bit key. Yes, 56 bits, not 64. I'll explain why in a moment. Think of DES like a very complex mixing machine. You put in 8 characters, and it produces 8 characters of gibberish. The same key that scrambled it can unscramble it. The diagram shows the 3 main components. First, your plaintext, the message you want to encrypt. Second, your 56-bit key, your secret. Third, the ciphertext, the scrambled output. DES always produces an output that is the same size as its input. 64 bits in, 64 bits out. Now, why 56 bits instead of 64? DES actually uses a 64-bit key, but 8 of those bits are used for error checking. They're parity bits. Each byte of the key has 1 bit that ensures the byte has odd parity. This was important in the 1970s when data transmission was less reliable. This fixed block size is both a strength and weakness. It is simple and fast, but it means DES can only encrypt 8 bytes at a time. Longer messages must be broken into 8-byte chunks. Modern algorithms like AES improved on this with larger block sizes. The Feistel structure. Now we get to the genius of DES. The Feistel structure, named after cryptographer Horst Feistel. This is like a magic trick that lets you use the same algorithm for both encryption and decryption. Here is how it works with simple numbers. Take your 8-digit input. Split it in half. Left equals 1 2 3 4. Right equals 5 6 7 8. Now, here is the clever part. The new left becomes the old right. The new right becomes the old left XORed with a function of the old right and the key. In our example, the new left is equal to 5678, which was the old right. For the new right, we apply function f to 5678 with our round key, resulting in, for example, 2468. Then we XOR this with the old left, which was 1234. If we are using simple addition instead of XOR for clarity, then 1234 plus 2468 is equal to 3702. So after round 1, we have 5678 and 3702. What's remarkable is that to decrypt, you run the same process with the round keys in reverse order. It's like a reversible puzzle. No matter how complex function f is, the structure guarantees you can undo it. DES repeats this process 16 times, using a different piece of your key each time. After 16 rounds of swapping and mixing, your original data is thoroughly scrambled. But apply the same process in reverse, and you get your data back perfectly. This elegant design is why Feistel networks are still used in modern cryptography. The mysterious F function. The F function is the heart of DES's security. It takes 32 bits, which is half your data, and transforms them in a complex but deterministic way. Let me break down what happens inside this cryptographic blender. First, expansion. DES takes your 32 bits and expands them to 48 bits by duplicating certain bits. Why? This allows the 48-bit round key to be mixed in. It's like stretching pizza dough. You're spreading the influence of each bit wider. Next, the expanded 48 bits are XORed with 48 bits from your key. This is how your secret is woven into the data. In our simplified example, if you have 110011 and your key bit is 101010 the XOR gives 01100. Each bit of the key flips corresponding data bits. Then comes the S boxes, the substitution boxes. These are DES's secret sauce. The 48 bits are divided into 8 groups of 6 bits each. Each group goes through a different S box, which converts 6 bits to 4 bits using a lookup table. These tables were carefully designed and controversially modified by the NSA to resist certain attacks. Finally, the 32 bits from the S boxes are permuted, or shuffled around, according to a fixed pattern. This ensures that the output of each S box affects multiple S boxes in the next round, creating an avalanche effect where changing one input bit changes many output bits. This complex transformation happens 16 times, with a different key portion each time. It's like putting your data through 16 different blenders, each with its own settings. 16 rounds of scrambling. Let's see how our simple number gets transformed through DES's 16 rounds. I'll show you actual values to demonstrate how thoroughly the data gets scrambled. We start by splitting the data into a left component of 1234 and a right component of 5678. In round 1, using our first subkey, the F function might transform 5678 into 2345. XORing with 1234 gives us new values. After just one round, we have left equals 5678, and right equals 3579. Watch what happens as we continue. Round 2 scrambles it further. By round 4, our original pattern is completely gone. The numbers look random. By round 8, halfway through, even knowing the original input and seeing the current values, you couldn't work backwards without the key. The table shows how many bits differ from the original after each round. After one round, maybe 35% of bits have changed. After 4 rounds, about 50%. By round 8, the relationship between input and output is completely obscured. This is the avalanche effect in action. By round 16, every bit of output depends on every bit of input and every bit of the key in a complex, nonlinear way. If you change any single input bit, about half the output bits will change, but which ones change will appear random. This is what made DES secure for a while. The diagram shows this cascading effect. A single bit change spreads like ripples in a pond, affecting more and more bits with each round until the entire block is affected. The fatal flaw: 56-bit keys. Now we come to DES's Achilles heel, its 56-bit key. Let me show you why this seemed huge in 1977 but is tiny today. A 56-bit key means 2 to the power of 56 possible keys. That's about 72 quadrillion. In 1977, if you could try one key per second, it would take 2.3 billion years to try them all. Even trying a million keys per second would take 2,283 years. No wonder it seemed unbreakable. But look at the timeline. By 1993, Michael Wiener designed, but did not build, a $1 million machine that could break DES in 3.5 hours. By 1998, Deep Crack actually did it in 56 hours for just $250,000. The cost per key tried had plummeted. Today's numbers are staggering. A modern GPU can try about 10 billion DES keys per second. With $1,000 of hardware, you can break DES in hours. Cloud computing makes it even easier. Rent some GPUs for a few dollars and crack DES over lunch. The graph shows this exponential improvement. What's particularly damning is that cryptographers predicted this. In 1996, they estimated that DES would be breakable by 2000, and they were right. The NSA reportedly could break DES even earlier. This is why key length matters so much. Each additional bit doubles the time needed to break the encryption. AES's minimum 128-bit key is 2 to the 72nd power times harder to crack than DES, that is 4.7 sextillion times harder. Other DES vulnerabilities. The short key wasn't DES's only problem. Several other vulnerabilities made it even weaker than its 56-bit key suggested. First, weak keys. DES has 4 keys that encrypt data into itself. Specifically, using these keys, encrypting data twice returns the original. There are also 12 semi-weak keys that form pairs where one decrypts what the other encrypts. While the chance of randomly picking a weak key is tiny, their mere existence was troubling. Second, complement property. If you complement, flip all bits, the key and the plaintext, you get the complement of the ciphertext. This seems abstract, but it cuts the effective key space in half for certain attacks. Instead of trying 2 to the power of 56 keys, an attacker might only need to try 2 to the power of 55. Third, vulnerability to differential cryptanalysis. By carefully choosing pairs of plain texts with specific differences and analyzing how those differences propagate through the rounds, attackers can recover the key faster than brute force. DES can be broken with 2 to the power of 47 chosen plain texts. Still a lot, but much less than 2 to the power of 56. The small block size, 64 bits, also became a problem. In modes like CBC, after encrypting 2 to the power of 32 blocks, 32 gigabytes of data, you expect to see repeated blocks, leaking information. Modern applications routinely handle much more data than this. These vulnerabilities showed that DES wasn't just limited by technology advancing. It had fundamental mathematical weaknesses that no amount of computing power could fix. Triple DES, the temporary fix. As DES weakened, the crypto community needed a solution. Enter Triple DES, 3DES, a clever way to extend DES's life by encrypting 3 times with different keys. Here's how it works. Take your plaintext and encrypt it with key 1. Then decrypt, yes decrypt, the result with key 2. Finally, encrypt again with key 3. Why encrypt decrypt encrypt? Backward compatibility. If you set all three keys the same, you get regular DES. The most common variant uses two keys. Key 1 and Key 3 are the same. This gives you 112 bits of effective security, 2 times 56, which seemed plenty strong. Our example shows hello being transformed into an encrypted string after the first encryption. It then becomes a different scrambled string after the decryption, with key 2, and finally a third encrypted string after the final encryption. But 3DES is slow, 3 times slower than DES, which was already showing its age. Worse, research showed that 3DES with 2 keys doesn't quite give you 112 bits of security due to meet-in-the-middle attacks. It's more like 80 bits, adequate but not great. The diagram shows why 3DES was always a band-aid. It inherited all of DES's problems, except for the key length. Still 64-bit blocks, still the same weak keys, where you had to avoid them in all 3 keys, and it was terribly slow for modern applications. 3DES served its purpose, keeping legacy systems secure through the transition period. But by 2001, everyone knew we needed something better. That something was AES. Lessons learned. The story of DES teaches us crucial lessons about cryptography and technology. Let's reflect on what we've learned and why it matters for today's encryption. First, let's discuss the critical importance of key length. The DES's designers knew that even in 1977, 56 bits was only marginally secure. They had originally proposed 64 bits. However, various pressures, including NSA influence and hardware limitations, led to the adoption of the shorter key. This compromise haunted DES for decades. Today's systems use a minimum of 128-bit keys, which provides a safety margin measured in billions of years. Second, the relentless pace of Moore's law. Computing power doubles every 2 years, but cryptographic standards last decades. DES was designed for 1970s computers but had to survive into the age of GPUs and distributed computing. Modern algorithms must assume attackers will have technology we can't yet imagine. Third, mathematical advances matter as much as computational ones. Differential and linear cryptanalysis techniques, unknown when DES was designed, significantly weakened it. Today's algorithms are designed to resist not just known attacks but entire categories of potential future attacks. The timeline shows the complete lifecycle of DES. It was born in 1977, began showing cracks by the 1990s, was publicly broken in 1998, and was finally deprecated in 2005. Yet, some legacy systems still use it, a reminder that cryptographic transitions take time. DES was not a failure. It protected data successfully for over 20 years. But its story reminds us that in cryptography, unbreakable always comes with an expiration date. Today's AES will someday meet the same fate. The question is, will we be ready with something better? Thank you for your attendance. Please consider subscribing to the channel.